We're gonna put you to work if you sit here.
This is a work tape.
Dwayne's going to announce that they're out there.
There's some
Kind of lost it. He's going to announce.
You can sit here.
He's going to come back 9:30.
We're just doing our streaming from here.
Chuck and I were out there.
What's 58? So, well, oh, just use the numbers, okay. While they're talking,
Oh, it's a chair.
do you have driver?
How you doing, buddy?
Yeah, doing better. I had a knee replacement this year.
Complete replacement. My wife had
Had to go really good surgery. Dr. Blake Thomas. Yes,
Did you follow up with rehab?
I got released from rehab this last Wednesday and started driving. Not legally. Monday was my next go practice driving.
That's amazing. Right. Oh, I had a friend of mine, he did in the physical therapy. I mean, they basically made him cry because he didn't.
Two cameras.
So they had him working, you know, he was not happy. Let me go find our
myself.
What'd I do? Door prize.
Yeah.
All right, let's see here. Huh?
Yeah, how are
Okay, cool. The bucket still should be back there. You'll get him to. By the way, thank you. Thank you.
I just want to go home that can appreciate it and use it better than I can.
Nothing wrong with that. And you get something made up for that in a minute. It's been 2 weeks. And the one starting coughing less, I got stuffy nose. So it's been.
Since I had COVID, I came out like 6 weeks.
So then, do I need to get my PowerPoint set up anywhere?
Oh, yeah, we need to make sure it's on there.
Yeah. Don't know what the best way would be to move it over.
Like me, I think it's just been.
I'll probably put my mask on once we get going after everything.
Just everything.
What do I do with the USB stick? Oh, there it is.
They might
Wait. Yeah, if I can figure out how.
All right, good morning. I think it's about that time. About time to get things rolling. What is it, 2023? I lose track of the years. So, Joe, I guess we'll let you get our event started.
Good morning, Bob Fest. You know, it's great for this event. We have been working since last year to put this together, and we're just glad to see everybody in person. This is the second live Bob Fest after the pandemic, before times, whatever you want to call it. We're glad that you're here. Look at all of those beautiful door prizes back there. I think we have a record number of door prizes this year. And you know what? We want you to buy as many tickets as you can afford.
Please.
Because we need the money. I'm just going to say it. Help us out, all right? And
Like a dozen eggs right now.
yeah. Gasoline too.
And we do take plastic.
We do take plastic now, thanks to Jeff. So for those of you who don't know me, I'm Joe Hefner. I'm a member of the Catawba Valley Astronomy Club. This man over here is David Breen. He's our current president. Would all the Catawba Valley Astronomy Club folks in the room here stand up? We have name tags. So if you have questions, find one of us and ask us.
We'll make up an answer.
The odds are pretty good that we'll know and answer. It might not be the answer that you want, but we'll tell you something. We've got a full schedule today. We have some fantastic speakers, and we have some food trucks coming to feed us for lunch. Lunch is always a good thing. And then we have some tabletop talks planned this afternoon. We are broadcasting live on YouTube, thanks to CVAC member Tim Slay over here. So behave while we're on the air, and that's more a reminder for me than anyone else. She knows what I'm talking about here. And we're going to start with some opening remarks from a representative from our host facility here, the Catawba Science Center. Please give a welcome to Dwayne Smith.
Be very brief here because I know we're on kind of a tight schedule. The main thing is, we've been the host site for Bob Fest for a number of years now, and we have a really good partnership with the Astronomy Club. So welcome, again, welcome. Thanks for coming by today. Important thing is, I guess some or all
Rest with the registration desk.
the passes.
Yeah.
So there are passes. These will get you half off the general admission. You don't have to, but if you would like to come into Catawba Science Center, our facility and tour around, see our aquarium, see a planetarium show. We have a dinosaur exhibit going on right now. By all means, do so. If you can find the time to do it. I know Bobfest has a lot to offer today, but we do close at 4. The actual museum closes at 4. So please stop by if you would like to do that. And again, this is what it looks like, and you can get one if you don't have one. Front desk.
It is worth the tour.
Yeah.
Pretty
So
awesome place.
we'd be glad to. But you have to go up to the desk, give the card to one of our check-in folks.
Are you going for an annual membership?
So about that, or you can do that. Second thing, very quick, we do have 3 programs or shows in our planetarium. We have an 11 o'clock, we have a 2 o'clock, and a 3 o'clock. The 11 o'clock is called Black Holes, the Other Side of Infinity. The 2 o'clock is kind of a kid show. It's about the Orion constellation and the Greek myth of Orion. And the 3 o'clock show is called Astronaut. So again, if you want to see one of those shows, that is in our aquarium and planetarium building, which is right up the hill. And get there a little bit early because it's first come, first seated. All right. And I believe that's it. The campus is a little bit complicated, but the big 3-story building, our museum is in that building, and it's also in the building I just mentioned, up the hill, the aquarium and planetarium building. Besides, of course, this building, which is called the West Wing. So if you're having trouble getting around, just ask an astronomy club member or ask a Catawba Science Center staff person. Okay. Anything else? I think the only other thing is I will be personally driving a shuttle during the lunch hour and a half. So for those with serious mobility issues that need to get over to where the food trucks are, I'll be loading up and doing a couple of back and forth at that time. Yes, food runs.
Where will the food truck?
Those are up again. We have, I think there's a map in the program, is that right? A map of the campus. But that is actually up sort of on the other side of campus. Yeah, it's kind of near the Methodist church. If you happen to see the Methodist church,
Yeah, that way.
it's sort of that way.
Bus parking lot.
That's
It's
not
a
very
what,
far.
5-minute walk.
Yeah, it's about a 5-minute walk.
Between here and the block and the end of the block.
Sure, but it's what I'm doing is just offering a shuttle service for those who have issues with walking up steps and that kind of thing. All right.
Thank you, Dwayne. Bobfest would not happen without the Catawba Science Center, so we're indebted to Dwayne and the executive director, Tracy Hall, for letting it happen. And out at the front, we do have some beautiful printed souvenir programs. There is some errata that we will be issuing in real time as the program plays out today.
And you have a digital, the QR codes on all your tables.
At each
Take a
table,
picture.
if you scan the QR code, Sydney's got one right there in front of her. If you scan that QR code, it will take you to the online version that you can download and have as a permanent souvenir of today's festivities. All right. In keeping with tradition, it is now my privilege to introduce the man, the legend, our raison d'etre, for those of you who speak very poor French. College was a long time ago. Ladies and gentlemen, Bob.
Well, I was trying to avoid that this year. These people get embarrassed here sometimes. Hold on, I'm hot in here.
It is.
You got something on there today, don't you?
I'm hoping.
Don't look away. It's not what you think.
Okay. The first year that this was an event here, T-shirt.
It still fits.
Got a little bigger.
But they like embarrassing me. Something that
Wait, let me see it again.
unfortunately we're having to miss now is and somebody used to come here that
Did you bring your trumpet?
all right. Jeff Norwood of Camera Concepts. He used to come as really a big vendor here on the way to Winter Star Party. I don't even know whether they're doing the Winter Star Party this year, but this was my 1996 T-shirt for the Winter Star Party. That was a great event. Hurricane didn't help much. Don Brooks, who was Steve Davis, I don't know if he'll get here. Don Brooks had to work all weekend. Steve Davis and Tom Brooks and Don Brooks actually kept this event going after Tom English, co-founder, left Gardner-Webb, went to Guilford College, Technical College, and, took over there. And we replaced the great Christmas show-off that the Carolina Skygazers put on. A little history behind it. There's other people that hadn't been able to make it because of health problems, surgeries, and all. I just had a new replacement December 12th, and it's doing great. But anyway, I'm not going to take it any more of your time. Let's get things rolling.
Thank you, Bob. Mike reminded me to remind you that there are now 3 computers going out of registration. So sometime today, we ask that you please digitally register. That's how we're going to keep a head count this year. We're going to get serious here for just a moment before the first talk begins, and I'm now going to turn the microphone over to our very own John O'Neill.
Thank you, Joe. Hey, y'all. I just wanted to get up here and announce that we're having an astrophotography contest this year. A few years back, at this very spot, Bob Eskridge and Barry Spencer and I were discussing the prospects of starting an astrophotography contest. And then the pandemic hit and put everything on hold. And since then, unfortunately, Barry has passed away, so we've decided to go forward with the contest, but name it the Barry Spencer Memorial Astrophotography Contest. Thank you. So anybody that brought pictures, I'm down at the end of the hall, second row from the end on the left. Bring your pictures down there, we'll put them on display. And I'm going to hand out tickets. Everybody take one strip. There's 3 tickets on each strip. So you get 3 tickets to put in whichever photo you'd like. And that's pretty much it. If you brought pictures, bring them on back. Did you bring pictures, Ronnie? Yeah, he's being modest. Okay, that's all I got. Thank you, and here's Joe back.
Thank you. One thing before we introduce our first speaker here, and that is that the Catawba Valley Astronomy Club did lose one of our own since the last Bob Fest, Mr. Barry Spencer. If you knew him, he was a very unique individual. I was his favorite bleeding heart liberal, and that was a term of endearment from this man. Barry was a fixture in many, many ways at Mid-Atlantic Star Party. He loved showing kids the planets through his telescope. I think that is the one thing that I can publicly share that I will remember about Barry. There were some other things that I probably shouldn't go into. But he was a wonderful man. He was completely dedicated to this hobby. He was an inspiration. And Barry, we miss you. And we know you're watching us today, so we're going to do you proud. And with your permission, I would like to dedicate the 2023 incarnation of Bob Fest to the memory of our friend Barry Spencer.
Yay.
Thank you very much for that. All right. Now, our first speaker is officially a regular in Bob Fest. Corianne Delgado is an amateur astronomer, a lifelong lover of the stars with a passion for learning and science. She and her astropup, Nix, did I pronounce that correctly? Enjoy many happy hours observing and imaging the skies. She works with NASA and the Jet Propulsion Laboratory as a solar system ambassador, and she is here once again with us this year to tell us about the James Webb Space Telescope and what we are seeing through the eyes of this masterful time machine. Ladies and gentlemen, Corianne Delgado.
Can we bring the lights down a little bit? Because I got pictures to show. Did they come down partially? Can we bring it down just a little? That's not my screen, is it? We need to switch this. That's not my screen.
You just need to plug it into the projector.
It's already plugged in.
Oh, I don't
You gotta
know.
do the source.
No.
Here.
There you go.
Oh, there we go. Oh, we're a little off. It's about pictures, so I gotta, show it. Oh, no mic. Okay, so if I need to get on the mic, let me know, but I do have...
It would be good.
Over here, you can hear me. I want these guys back here to hear me.
Yeah, no, this one means.
All right. Yeah, microphones make me nervous. So you let me know if you can't hear me. I do like to talk loud. Okay, I'll use the mic. Okay, how's this? Better? All right, okay. Oh, I can't believe I'm here as a keynote speaker. This is really cool. I have to tell you that I first came to Bob Fest in 2007. Ooh, it's too close to that microphone? I'm not sure. And it was a bit of a moment in my life because I just joined an astronomy club and I was inspired by all this education that Bob Fest had. And in doing that, it started launching me into astronomy and learning about the universe, not just behind the telescope, but all this extensive material. At the time, there wasn't a lot available. Now you can find a lot on YouTube. So I just wanted to say thank you for all you guys for inspiring me to get where I'm at now, that I am a professional astronomer, which I'll explain in a minute, but I'm a professional astronomer and I love to talk to the public and working with NASA and JPL as a solar system ambassador. That's just really cool, and I wouldn't be there without a lot of you guys here. So we're going to talk about the telescope through James Webb. I'm going to pull this down a little bit. I feel like I'm really loud. For starters, I am a solar system ambassador, and I wanted to let you guys know that if any of you are space enthusiasts, you can also be a solar system ambassador and receive special training from NASA, science mission personnel, scientists, and all kinds of things. It's really great. We're all over the United States, actually all over the world. John is also one, but that's why I'm here to talk to you. So let's tell you what I do in my day job, or my evening job. My professional astronomer role, I give a show, if you must, at Primland Observatory in the Blue Ridge Mountains. I don't know if you can see my cool dome there. Let me get it closer. It's a 30-foot ash dome. It's really fun. That's my bragging points, because the telescope is only a 14-inch CGE Pro. We give a live show every night, but I love talking to people about the stars up there. So just a little bit about me. I'm going to talk about Hubble. Anybody recognize this guy? Okay, well, James Webb is the next generation. And for this presentation, I'm not going to go over a lot of the intense science details of the machine itself. I will touch base on it so we can have a base of things, but I want to show you pictures. And they only gave me 45 minutes, and I don't want to talk too fast. It's 9 a.m. So Hubble was the next generation for this, of the great space telescopes. It's bigger, it's better. So if you're not familiar with James Webb, which I'm sure most of you are, but we've got, a 2.5 meter, 2.4 meter mirror on Hubble, and of course, a huge 6.5 meter with 6 times as much viewing area on the James Webb. And James Webb is engineered to take pictures at very cold temperatures so that we can see the heat of the universe. It's huge. So let me just give you a quick overview in case you don't know. We've got the ISIM, which is the Integrated Science Module. Sorry for your feedback there. That's where all the good cameras are, and that's where all the science is being done. The spacecraft bus underneath the sun shield is where all the communications and all the brains are coming from, and they're projecting the information back to Earth. The Kapton is the shield, so it's a very thin material like mylar. I'm not going to go into, like I said, extensive information about it because there's a million videos on the internet, but it's really cool because it keeps the telescope very cold, about 30 degrees above absolute zero on one side, and it's, 800 degrees on the other side? 800 Fahrenheit. I don't even know what that is in Kelvin. I should have looked that one up. And then we have, of course, that beautiful optical mirror, the beautiful gold mirror with its 18 segments, hexagon shape. It's really cool, but it's big. Okay, so we're gonna keep moving on. I wanna talk about what James Webb sees and why it's a little different from Hubble. Hubble sees in a very small bandwidth of light, visual light mostly. Spitzer did see a wide range into the infrared, very deep infrared. However, the mirror was very, very small, so we weren't getting the same kind of detail. With James Webb, we're seeing just a little bit into the visual and then way into the infrared. And with that huge mirror, we're able to resolve details. The microns, the arc seconds, are just incredible. They're just so detailed. You'll see as we go along. We'll talk a little bit about the spectrum as we go on. One thing that I have learned since I've been doing this is about the science. Now, when people think of James Webb and they think of NASA, they think that NASA's the one putting out all the science, and it's not. James Webb is a telescope for everyone. For anyone in the world could actually petition for time on James Webb, which is really kind of interesting. Easy? No. You have to have a very detailed proposal about what, when, where, and how, and why you want to do it. And then if you get approved, then you have to tell it what guiding stars, where do you want to view, what's the aperture. So it's very difficult, but I would love to see like a school students, maybe some seniors in high school petition for times on James Webb and get it. That's one thing I think would be really cool. So anyway, all of the data that comes from the Great Space Telescopes goes to the Space Science Institute. And it lives in this Mikulski archives for space telescopes. So when the data is released from James Webb, typically after a year, because you do get a year of proprietary viewing of the image, but if you release them earlier, they'll go on here. All the information is on there, so you can download the raw data yourself, like from Juno or Hubble, and process it and even do your own science with some of it. So I thought that was really cool because I know I'm struggling with astrophotography, and that's a good place to play when it's cloudy, if you must. I've got some links on the table. One of them is to archive, and there's another link on there I think that tells you how to do some of this stuff because it's kind of complicated, but it's good. It's just really interesting. So let's keep going here. I want to talk about the 6 data collection components because they're important to the pictures you're going to see. Sorry, too much coffee this morning. So, the aperture masking. When we're looking at these bright objects in space, we might need to tone them down. And if you're not real familiar with what aperture masking is, if you're an astronomer and you're looking at the sun, you're probably very familiar. But you're lowering the amount of light that's coming into the picture to hit the camera. Kind of akin to when you put your hand over your eyes and you're looking when the sun's out so you can see a little better. So James Webb has 6 of these components integrated into some of the modules. There's a micro shutter array. Now this thing is incredible. It's got about 250,000 tiny little micro shutters that are only about the size of the width of a hair, a human hair, and they all will take pictures. They'll take the spectrum of a bunch of objects at once. Sorry, it's kind of hard to describe. So if you think of a lot of stars or a lot of galaxies in one field, you can take a picture of each galaxy and get a spectrum from each galaxy to see if it's coming or going or what elements are in a particular galaxy or not. spectrographs. And if you're not familiar with that, that's the spectrum where we're going to simply divide the rainbow and look for the fingerprint of the chemical element that's there. Now, the integral field unit, sorry, I keep struggling saying that, is basically a combination of pictures with the spectrum, and I've got a really cool animation I want to show you because you always hear about these complicated cameras on James Webb, but I don't know if you realize how complicated they really are. And then the coronagraphs, and this is where we're going to block out very bright light from an object, usually a star, but I've actually seen them do it on a galaxy. Where they will block out the light of the star to see things close to the star that you normally couldn't see. Okay, we're like, come on, can we get some pictures? So, just to go over the cameras real quick, you can read that we have a fine guidance sensor. And by the way, this fine guidance sensor, this is your guide camera. And for those of you who do astrophotography, this thing can see basically the side of a dime at 1 kilometer away, and it holds that spot. And it does that so that the camera's not moving around when you're taking picture after picture. And it's also got the slitless spectrograph, which I'll show you what that is in just a minute here. For those of you who do astrophotography as well, you think your filter wheel's bad? Look at this filter wheel. It's pretty insane. I don't think I would want to mess with that too much. We have near spec, which is one of the, we see most of the images coming from near spec. It's also, I believe, one of the coldest ones that's out there. And it has the micro shutter array, the spectrograph, and the integral field unit. And there's no sound on this. See if it'll play. There we go. Oh, don't worry about the sound, it's just the ESA logo. But I wanted you to see, this is one of the units, the near spec unit. Watch the light as it comes in from this, and this is just the coolest thing. So the light's gonna come in. I wanted to cut it down, but I'm not allowed to. See the filter wheel on there? So light's coming in from the secondary mirror. So the big gold mirror will capture the image, capture the light, project it to the secondary mirror, and then come into the unit, and then start bouncing around. And they're doing this so that they can separate out the values of the light so they can see the spectrum. You're going to see a point in here where they really cut it up. Have you ever tried to look at the back of your head with a mirror? I'm just like, how many times did they have to push light through this to get this? And then they bring it all the way down to this. The 4 sections, though, is actually another piece of the camera. It's still bouncing. I promise you I won't kill you with these videos. There's 4 of them, so you can watch them all on the internet, but this is so cool. Look how it cut everything up so that it can really divide that spectrum, bounce it around again, and then you're going to start to see it coming out in all the colors. Yeah. So next time if you do astrophotography and you're having a bad night, think of that. What this really is doing is allowing us to see segments and get spectra from each of the segments, because the core of a galaxy is going to be brighter than the arms, and you're going to have different materials. It's going to give you the full color range, the spectrum on it, and then they're going to combine that to give you something with more of a natural color. Now, I hate to say it, but all of the images from James Webb are photoshopped. Now, that's not a bad thing. You have to, because you're not looking in what we see as visual light. So it's taking those layers and assigning the elements that it's seeing and the bandwidth that it's taking into a particular color. Okay, continue on. We talked about spectroscopy. So this is where we're breaking down that light to see the fingerprint of the element, and these are the absorption bands, I'm sorry. I keep doing it backwards. So you can see that hydrogen has a very distinct fingerprint. So when you say, how do they know that star is made out of carbon, or how do they know that galaxy is older or younger, or primarily has a different element in it, this is how we know. Everything has a method to its madness. Okay, I think this is one of the last ones. So you have near cam. Why does that feel like a duplicate?
Lose any, the light coming in, lose any intensity or
I'm sure it does. You have to think it does after bouncing around so much, but that's not a question I've ever asked.
That light path is so long, it seems like there's a time delay.
Yeah, if we did it in real time, it'd be a lot faster.
Is gravitational
Gravitational lensing?
Is it incorporated in any of this process, or is that another?
No, it's a separate process, and I'll actually be able to touch base on it at the end if we can make it that far. I got a lot of pictures, so I'm trying to move fast. So unfortunately, I don't have all the good James Webb pictures. I chose the ones I could either talk about or that I really love myself. I encourage you to use the materials that's on the tables. There's some links to some stuff. Go to the James Webb website and look at this stuff because you really want to zoom in and read about what's going on. So here's an example of that coronagraph, and this is where we've looked at a young star that hasn't formed its solar system yet. It still has a dust plane going around it, a protoplanetary disk, except that it's got a star on it now. So they blocked out the light of the star so that we could see things closer. When we look at planets now, we have to look kind of far away from the star, but not too far, because we've got to wait for it to orbit to watch the dip in the light. So if we pick something that has an orbital time of 80 years, we're not going to be able to verify anything for 80 years. So we look close, but that's really hard when you've got a planet close to a bright planet close to a brighter star. And we really don't have any luck with dim planets. That's why we always find hot Jupiters. But here, in two different wavelengths, we're seeing the dust plane, which is really cool. I didn't see any actual planets. I didn't have anything called out to me as planets on here. But what was called out was that the blue wavelengths, which is a shorter bandwidth, I can give you the actual bandwidth on here, but it's showing more reflected dust. So this is a very nutritious solar system, if you must. In other words, it's got a lot of material that can coalesce and meld together to make planets or other body systems, moons and asteroid belts and everything. I thought that was really interesting, but that's to show you the coronagraph. The MIRI. Now, MIRI is really cool because it's got the biggest range of view, and it's going to give you some really weird colors, really ghostly effects when they color them more towards the natural color that they would see, even though it's not colored. It's also running, it has the lowest resolution, but it's also running, I think, colder than everything else. It has the coronagraphs as well. They almost all have the spectrographs. So now we're getting to the good stuff. Okay, so this was an image that was released just 4 days ago, on the 23rd. Now, when you see these pictures, you may see them again in 6 months because we discover NASA, some scientists discover something new about it. When we look at this right now, we can see a lot of hydrogen in here because there's star formation in this one area. See if I can get it. In here, we have a lot of star formation. And when they looked at this in the spectrum, they actually saw a lot of complex minerals that are ices, which was strange. And that's good because that's a good way to produce planets, is those complex ices. So this is the visual picture that we have from this, and here's the spectrum. And I know you can't read it from here, so I just want to zoom in on one part where you can see that we've got methane and methanol and ammonia all building around this star birth area. So we're going to have a nice, rich, complicated solar system coming out of that star. And that's the combination of the visual and the spectrograph. Who doesn't love Jupiter, right? That's one of my favorite things in the whole solar system, in the whole universe, I'm going to say. We weren't sure when we put James Webb on it what we would see because Jupiter's very bright. If you've ever looked at it, it's bright in the sky. Everybody knows, what's that cool star up there? And so we got a picture of Jupiter, and this is kind of a nicely colored picture. I want to show you another one, but here you can see the rings around Jupiter because all of the gas planets in our solar system have rings. You can even see a diffraction spike down here from Io, but you can also see the aurora. But they hide the good stuff in some of these public pictures. This is the one that you saw more in the news. This is the one that I like because it really shows you kind of what's going on. Now the green is a real element. It may not necessarily be green because that bandwidth of light was given a green filter, but yes, there's another element that's around the pole areas, probably excited by the aurora that's happening, and that's the orange spots that we have up here. So let me get in here a little bit. So see at the top we have aurora, and I don't know how well you can see it from here, but you can see the orange banding kind of wisping across the top of the planet. We're looking at the aurora instead of ultraviolet like we did with Hubble. We're looking at it infrared, and we're still seeing it, and we're seeing it way above the atmosphere, which is really kind of interesting. And I don't know if you can see this either. It's hard to see over here, but there's almost like I like to say atmosphere. It's not an atmosphere because Jupiter's a gas giant, but it's almost like there's a haze layer around the planet. Some people said, oh, that's an error of the camera, and it's not. It's actually a real feature, so that was something interesting. Oh, what I was saying, the science from these pictures, sorry, I forgot about that. The science from these pictures may get more detailed in 6 months or even a year because you have to take time to analyze it. You don't just look at the picture and go, oh my gosh, we just discovered a whole bunch of new stuff. It takes a little while. Here's another interesting part. Sorry, oh, go back. On the tops, these little squiggly snake-looking things, those are akin to thunderclouds, if you must. They're very high-level clouds, and they're very reflective. You're not seeing reflected light, you're just seeing a different absorption. But look at the detail that we've come up in the picture. I think it's so exciting.
Like cirrus clouds?
Well, more akin to thunderclouds, because they're more like the thunderhead that you have coming up. It's very high altitude. And like I said, this is why I want to encourage you to go look at these websites and really zoom in on these pictures and take them for every little piece you can, because there's so much detail in them. So another body of our solar system, Neptune. We haven't done Uranus yet because we're not in a good aiming position for Uranus. So here we have Neptune, and you've got the bright moon Triton at the top with the star diffraction marks, and that comes from the hexagonal mirror. You can actually see the spaces in between the mirror in this picture. But you can see Neptune down here, and what's really nice is that you can see the storms that are happening on Neptune. And keep in mind, we really haven't had a really good detailed picture of Neptune in about 30 years because it was Voyager taking it when they passed by it. We had, Hubble taking images, but not a nice, good, detailed image that would show us the surface, not the surface, the gassy surface, and the storms of the planet. And you can see 6 of its 14 moons there too. Here we can see some of the cloud tops and a little bit of the surface of the changing features of Titan, which is a moon around Saturn. Keck actually did some combination and added to this data, and it's even kind of cooler, but I just love that you can see the clouds and all the pretty, it looks like a cell to me. And the surface features are changing too, by the way. So Stephan's Quintet, or Stevens, it depends on however you've heard it, one of the first few images that was released. This is also one of the largest resolution images we have, so it's akin to like the deep field, except that it's not deep field. It's 5 interacting galaxies, and actually 4 of them are only interacting, but the picture's just amazing. And this is a composition, by the way, of 2 of the cameras because we can combine the images to make a better image, and you'll see as we go along. So if we zoom in, these 4 galaxies are interacting. The one at the bottom is actually rapidly moving in towards the others, and that's why it's creating this bow shock here. This is an area of accelerated star birth because of its acceleration into the other galaxies. So like Andromeda, it's coming towards us, but it's kind of ambling towards us. So we're not going to see this huge disruption and crazy star formation where we interact. But here, because that one galaxy has such an accelerated speed, we are seeing that, and you can see the star forming in there. And if you look at the top one, we've got a really active AGN, or black hole with a lot of material being dumped in it. It's causing these beautiful arcs of material to be, they're not from the black hole because you can't get anything out of a black hole, but it's causing the galaxy to throw up its arms, if you must. And I haven't been able to get an actual explanation as to what they think this is yet, but I just love the details that you can see. And if you notice, if you're looking in close enough, look at everything in the background. The star-shaped stuff is stars. They're bright objects. Anything bright's going to give that the diffraction marks. But look at all the galaxies behind the galaxy. That's just amazing. It's mind-boggling. What do we have here? Sorry. Cosmic cliffs. Don't you just love it? I have this picture up on my wall, but now I need to get the new version of it. So here we have a big starbirth region in the southern hemisphere, very well-loved picture area. Hubble did some great pictures of this. This is just the near-count filter on it, and as you get in closer, you can see where we have nodules, these pillars of starbirth. So you have a hot star that's glowing in there, except right now we can't really see it because we're only looking in one wavelength. Well, actually, there's 5 wavelengths we're looking at here. but you can't see what's going on behind these clouds because they're blocking the light. So we're going to go look at the heat with the, I think it was Miri is what they used. Yeah, Miri. So this is Miri where we're looking at the heat signature of it. And now we can see all these little stars popping up in the background. See, I don't know if you can see them from here, but all these little red dots in this bank of clouds. And this cold bank of clouds is cool gas that's, as it gets closer and starts combining and forming stars, it's going to get hotter, and then the winds kick up as the star is being formed. As those winds kick up, and I mean they kick up, we're talking millions of miles an hour that the stars... Sorry?
How do you distinguish between the stars that are in star-forming region versus the stars that are in front of it, that are closer to us?
The fraction marks really, because if they're in it, they're not going to be that bright. But they could probably do... This is in our own galaxy, by the way, so it might not be far enough to actually see a redshift to get on the distance, because once you're on a galactic scale, redshift is not the way to measure distance. But yeah, the ones that are spiked are probably in the foreground, or very bright stars that are sitting in front of the dust cloud. Yeah, and you can even see the bow shock here in this area. I think I zoom in a little bit, but I don't know if I zoom in there. No, I zoomed in over here. So here you can kind of see a bow shock where you have these high solar winds pushing the gas around. And it's making these beautiful clouds, these cloud formations. Actually, you can see it over there. I like the one here because it looks like a little comet going through the area, but it's not. You're only seeing part of it. But you know, sometimes when I'm trying to impress somebody, I'll tell them it's a comet because they don't get it. So we got VV191, yeah, 191. We've got a pair of interacting galaxies. Now this is interesting to me because when you see an interacting galaxy, usually you see them pulling on each other. So I'm trying to figure out how these are running together. Like, are they cartwheeling in together and just one's a little in the foreground and one's in the back? And I've been trying to find out more information about them. But I had to show you that one of them has these very prominent dust lanes. And whenever you see structure in a galaxy like this, you see these clumps, you know, so spiral arms or dark bands, you're going to see star formation. So it's very active with its star formation. This one is kind of hazed out, which means it's an older galaxy, not producing stars quite as much. And that might be why there's not that weird interaction that we normally see when we see a colliding galaxy. Now, if you do we call it the James zoom, or the JWST zoom, you notice there's a weird brightness in the corners of the galaxy. That weird brightness, I think I zoom in a little more. There you go. I figured it'd be good for you guys back there. That weird brightness is another galaxy behind these galaxies that they're enlarging, they're magnifying. So this is your gravitational lensing. So this galaxy is probably right behind the core, but the gravity from the black hole and all the mass of the stars is causing it to bend the light so that you can see around it. And we'll see more examples of this as we go along. But that's really cool. You can actually do this in the next solar eclipse when we have one next year. You can plot stars in the sky and take images, and then take another image later on, or plot where the stars actually are, and overlay them, and you can see how the stars will actually move from the gravity of our own sun. Sorry about all the mic shoot. Gotta love this guy. So this is probably one of my favorite pictures. I just think it's so cool. So this is from a dark nebula. A dark nebula is simply an area where there's a lot more dense gas and dust so that you can't see the stars and the starburst going on. There's nothing illuminating our point of view from it. So here, when you really zoom into that dark nebula, you see a little wisp, like the one I said looked like a comet. And here you have a protostar. This star is about 20 to 40% of the mass of our sun, or ultimately will be. It's not a star yet. It's literally an embryo. It is only about 100,000 years old, they estimate. And what you're seeing on the dark sides going up and down is dust and gas blocking the light, but then it happens to get thin in these side areas. And the red side is thicker than the blue side because the blue light is blocked by the gas, so that the red side will glow red, but where it's thinner, it's going to glow out in blue. And I was wondering, I'm like, okay, we see these clouds coming in. Are they coming in or are they being blown away? And it is being blown away. So the wind speeds from these new baby stars are pushing pushing the dust away from it, even though we have material is collapsing onto the star. And I don't know if I zoomed in again. Yeah, I did. You can't even see the baby star because it's behind this little dust thing. So we're seeing it edge on like our Milky Way, and he's right in there. And he's got all this. Now, the distance here, I was trying to get the distance, and I saw two different numbers, and you're going to laugh at this one. 17 astronomical units and 17,000 astronomical units. So I can't tell you the real distance on what you're seeing in the visual, but it does appear to be quite large. It's a beautiful star-forming region. Oh, I love this one too. So this is, have you ever heard of a Wolf-Rayet star? That is a star that's about 25 more times massive than our own star, so a very high mass star. They're so massive they produce a lot of chemicals that the normal stars don't, even big stars, normal big stars don't produce. So here we have a pair of binary stars, one of them being a Wolf-Rayet star, which has all these extra chemicals in it and everything. Extra elements, I should say, and it's rotating with another star, and then when they get close enough, the two stars interact, and because the Wolf-Rayet star has what it needs to make dust, because hydrogen doesn't make dust on its own, you have to have other things added to the mixture. So when the Wolf-Rayet star drops in and gets close enough, it changes the elements and starts forming dust. And so what we have in this picture is concentric dust bubbles, if you must. They're not rings, they're actually bubbles of when the stars orbit each other every 8 years and they get close and they kind of sneeze out some extra dust. And then they go around and sneeze out some extra dust.
Sort of like rings on a tree.
It is, except that we're seeing like a head-down view, so we're not seeing the bubble, we're just seeing the rings. But this is, if it's once every 8 years, this is 17 rings that we can see. That's over about 125 years of history that we can see in the sky here, and all this dust formation. It's just mind-boggling. How are you doing on time?
You're good.
Oh, good. I do have extra stuff at the end, but I figured you might have some questions, and we're not done yet. So the Tarantula Nebula. Now, if you don't know, they named this the Tarantula Nebula because of all the wispy finger-like appendages that it has, so like a spider. As an astronomer, we like to name things like we see them because we can remember that. Everything has a million names, catalog names, common names. So if it looks like something, we try to just, Ring Nebula. You know, Gerald, what I'm talking about? Oh, yeah, I do. Okay. Never mind the NGC. So anyway, so we have this Tarantula Nebula. Now this is one of the biggest star-forming regions that we know of in our galaxy. It's actually, is it in the large Magellanic Cloud? It is, yeah. So it's not really in our galaxy, I should say, but it's the biggest one we can see. There may be bigger ones in our galaxy that we don't know of, but this is the most active, the largest field, even bigger than Orion, and it also harbors the biggest stars that we know of. So I think the largest star that we know of at all is in this area, and I don't know the name, I'm sorry. So when you're looking at this picture, and I think this is from NearCam, sorry. You can see the red dust. The red dust is actually very cool dust in that area, so it hasn't changed enough to it start emitting new light. So we're seeing it in the red. When you zoom in, you can start to see some of these star formation areas and the huge masses of stars. Could you imagine if in our galaxy, everywhere we saw globular clusters, there was this before the globular cluster came? Wouldn't that be amazing? So we have another star foreground. Oops, sorry, I didn't mean to do that. I got a little click happy. Okay, so we have all these star formations. This is a hotter gas that we see in here, and then a big stellar nursery. Like I said, to me it looks like it's the beginnings of a globular cluster. However, globular clusters are very old, so that doesn't quite make sense, but that's what I see when I look at it. I wanted to show you the MIRI part. This is the MIRI portion of the picture. The others are combined with NearCam. You can see those diffraction marks and the 4 millimeter division between each of the 18 mirrors. That's why you see the little dark spots on the diffraction marks. I love how MIRI gives you this eerie glow and everything. It's because it's not looking at heat, it's just looking in the infrared. And so we're seeing the blue, which is one area of the infrared, and the red being another bandwidth of the infrared. Now, I didn't want to touch on planets too much. They're not my favorite thing because I want to see a picture of a real, I mean, I've seen some, but nothing that was like, wow. So right now, when we look at exoplanets, we're really looking at we're looking for them and looking to see what's in the atmosphere. So when you have a bright star and a planet goes in front of it, you're going to get a little light dip, a light curve. And that's what we have here is basically all the light coming in and it's different points, so they average it out. And then when the planet goes in front of it, you see the dip. Now, you can also see spectrum, which I didn't include in here, which is too much for 10 o'clock in the morning. But you can see the emission bands of all the elements that might be in that atmosphere. And James Webb is finding some really interesting elements in atmospheres, ones we didn't think we would be seeing in the quantities that we're seeing. The Phantom Galaxy. This is one of my other ones. Now, Judy Schmidt, you might have heard her name by now if you do science news at all, but she's the one who edits a lot of the images that come from James Webb. And you know what's an interesting thing is she's just an average person. There was a contest to edit images, and she came in third of all things, and now guess what her real job is? She edits the pictures off of the big telescope. I think that's really, really interesting. But she really brought the details out in this where you can see these star formation. These are clumps of hot gas where stars are being formed. The stars are in the red. The gas, the cooler gas around them would actually be in the blue and the white. And the one answer I couldn't get is what's going on in the middle? Does anybody know? John, maybe? I know we're going to have a supermassive black hole, but why does it look like it looks? That's what I don't understand. But beautiful picture. No, I mean, are you not excited about this? And we're seeing, the reason why we like to study things like this is because we want to see the galaxies in different phases so that we can understand more how our galaxy was formed. That was one of James Webb's primary science goals was how do galaxies form in the first place? Because we really don't know. I still want to know what's going on in the core. I mean, why? Is that an accretion disk of a black hole that we're actually seeing? I just can't find any data on it. So I'm hoping somebody will do the analysis in the future.
Very hot stars going out.
Yeah, you would think, especially if, being in the core, you couldn't see the accretion disk around the black hole, I think, at these distances. But maybe. Now, just to give you a visual of this redshift, because it's a little hard to understand. We all know the Doppler, the ew, how an ambulance sounds when it gets closer, and then when it gets farther, the sound changes. That's what the light is doing too, and I like to actually show it because it doesn't make a lot of sense when you think it's shifting. And so if you look at the cutout, I know it's a little hard to read, but the top galaxy is 11.3 billion light years away. And you can see oxygen and hydrogen in there and where they fall in the spectrum. When you start getting a little older, you're going to see that oxygen and hydrogen start pushing away. And that's because the light is having to travel longer and longer distances. So it's going from, I can't even see it, the wavelength of light, I don't know what those numbers actually mean. They look like 2 and 3. It's moving all the way out, and that's giving us the time distances. I was trying to look up some more information about what do these mean, because somebody was saying that they found something that was 16 shifts of light. And I was like, okay, my brain's going. Do you know?
So lowest redshift, I think the letter Z is for it, and it's like a fraction of basically like a multiplier number. So 2, 3, 4 is how many times the Z it is.
All right, is that where it stopped out at about 10 or 11? Because somebody was saying that we found something that was 16. And I was like, what does that mean?
Yeah, so like the standard Z number, whatever that is.
So let's take a look at this. I'm sure everybody knows the SMAX galaxies. One of the first images. Now, when I hate to say it, when Biden first introduced these, he said it was a grain of sand at arm's distance away. You know what? It's not. It's a grain of sand at arm's distance away. He probably didn't think that, wow, we could see that. So what we have is some galaxies 4.5 billion light years away, and then we have our spaghetti. That's our spaghetti. That's that gravitational lensing, and that's because the mass of these galaxies in the core here, is changing the light, bending it, and giving us our funhouse galaxies. Now, how do they know that that's all the same galaxy? Because most of those are the same galaxy. Not every one, but most of them are. And when they looked at the spectra and the distance and the speed, it was all the same. So that way they could say, that's the same galaxy. And here's a nice close-up view of it. And I think that's where it ends, because I want to leave you out there in the galaxy. I don't want to go too far, and I want to leave time for a couple of questions about anything. You guys still awake? Any questions? Are you... No questions?
So, what did I do? James Webb, Hubble has gone way beyond what expectations there were. This amazing telescope. What do they expect James Webb to be able to produce over time?
If nothing goes haywire, right now I'm hearing 20 years, which it was originally about 5. There is a finite limit, though, to them, because there is an closed system. I want to say it's a coolant, but it's something that they can't, do you know?
Fuel.
It's a fuel, but it's...
The position correct?
Yeah, for the positioning. That's what they say, that, we could probably get it to stretch out maybe 20 years, so we're hoping for 19 more. But it could change.
The meteoroid impact that hit the telescope last year, how much effect did that have?
They're able to correct it, kind of like with adaptive optics, but what they did was they started up a program called MAZ, the Micro Meteorite Avoidance Zone. So what they do is they only view about 39% of the sky at one given time, so they do an arc. They don't look away from the sun, and of course they don't look to the sun, but they look at an arc like this. So over the course of 6 months, they can actually see 100% of the sky. But if you want to look at an image over here, you have to wait for it to get into the zone, because they avoid areas that are going to basically drive micrometeorites into the mirrors. But really, they couldn't fix it, obviously. The Hubble's not repairable, but they were able to make adjustments with the mirrors, because luckily they have 18 of them, so they can kind of just block one out.
Have they had any other indications?
I just heard that I was hitting a news story, and I didn't get enough details read it, but somebody said that they pulled NearSpec offline because of something being out of alignment. And I don't think it's permanently down or anything, but I think they have to recalibrate some stuff on it.
That's not to do with micrometeoroids.
No. At least I hope not.
Does the telescope, does the entire assembly, does it move at all? Is it motionless?
It's motionless. The mirrors can adjust, and NearSpec, I believe, is the one that, NearCount, I think, is the one that helps adjust them, like takes the pictures. But the telescope itself is solid, and it's floating in space, and then it has little correctors that will help it line up, so that when a guide finds a guide star at a target, it's going to hold it there.
I take it the whole assembly does have the ability to move somewhat or rotate.
Yeah, with the little jets. They can look at a path of sky like this, so we can turn. It's at an L2 spot in the sky, which I don't know if you know is an equilibrium spot where we're not getting a lot of push and pull, so we can use minimal fuel. But yes, it's got to move a little bit to look over here, and then it's going to move over here. And because everything is plotted and planned for a year in advance, they'll probably take their time and go over. I don't know if you've ever had a big telescope dome. You don't go from here to here. You're going to waste a lot of time moving. That's what I have to do. It's like we have to start with star birth and star death and then go see these other things. Any other questions? Yeah.
It was a question from earlier. How do you tell, you explained how to see the stars in front with the refractor pattern. How do you know if one's behind it or past it?
If it's a star, chances are you don't know. Standard candles, so you have to think of how big is it and how bright should it be. So you'd have to be the scientist looking at the data to figure out if it's in front of it or behind it. But that's one of those reasons why the website is really good. And Twitter, oddly, there's a bot out there that tells you what James Webb is imaging right now, which is really fun. So it just automatically generates, hey, right now James Webb is imaging this. But with Twitter, you can ask those questions to the scientists and say, I want to know this. Like, I'm going to ask them about that black hole region. Does that tell us anything? I love black holes, but I don't understand them at all.
Where do they plug it in?
Where do they plug it in?
It's solar.
Actually, there is some, isn't there some solar on it? I don't remember seeing any solar panels. I know it's got something, so no? It's got to have solar. It does have batteries. I don't know about solar. I don't know, I've never thought about that. Now I have something to Google when I get home. All right, thank you guys for listening to me today. I told them, don't put me this early in the morning again. I worked till like 2 a.m. Who else was out last night trying to find that comic? Yeah, 2 a.m. Oh, gotta get up at 5. Okay, I'm here. So thank you for joining. And you know what? If you want to know more, get out there and look and ask and talk, because there's an entire universe of wonderful things out there. I just love it. Yeah.
That is one of the best science talks I've heard recently, and I just got back from a conference in Portland, Oregon. So
He's buttering me up. It was really awful.
room full of physics geeks. So that was. Thank you so much, Corinne. Okay, we are right on schedule. Exactly. We have a 15-minute break here until our next speaker takes the podium. I was told just a few moments ago that Siri is talking to me. The donut truck is here with hot chocolate, cider, and there's some other, I want to say like espresso or something, some other fancy schmancy hot beverage.
Ready at 11.
That, ready at 11.
Ready at lunchtime.
Okay. The other thing, please remember to buy door prize tickets, because we want everybody to walk away with something, including the door prize out there in the lobby. We want everyone here to sign the door. Someone is taking that door home because I'm tired of it being in my garage. So get rid of it, okay? I'm tired. Things have been in my garage for 2 years now, so it's literally off of my house. So let's take a 15-minute break, mill around, buy door prize tickets, get a program. There are some corrections to the program that we will be making a little bit later on. So,
Do you want to pay for this?
do what?
Do we want to pay for this?
What?
Do you like the brochure?
Yeah.
Help us pay for it. Buy 500 door prize tickets.
He's exaggerating. 250 will be plenty.
467 precisely.
We'll be back in about 15 minutes.
about 2 minutes to our next presentation. We got about 2 more minutes.
I grew up in Shelby, right here in North Carolina. Not very far.
Good.
This is like being back home. I'm trying. As far as I'm concerned, I'm actually my mom, so you know about.
No. I've got a couple scopes.
So are we putting out just the screen and the audio, or I'm switching? So you're switching back and forth? Okay, cool. I just didn't know how you were set up.
That's the podium.
And you're just going back and forth with it. Cool.
I'm bored of being.
I am so sorry.
I'll tell you my reaction. Yes, that is the key.
Yes. A lot of times, in my practice, any given year, I have I've noticed in the last 5 years, 8 years. Yeah, Connecticut's up there. I mean, you obviously get your Pennsylvania. That's Connecticut's that's the only yeah, just high cost of living.
Somebody out there creating just come in, you can see it, and that's what's funny about
He was down there. You want me to get ready? All right, guys, it's good to have a seat. It's time to get started with our second half of our morning program.
what you're doing on the Friday. I mean, Friday evening.
Testing, 1, 2.
Yeah, you're probably off camera, right? See, guys.
I can hear Joe. I can't hear anybody else.
It has come to our attention that out there on the World Wide Web, over the last couple of weeks, there have sprung up some websites that are somehow publishing today's schedule, and the information there is wrong. Like, for example, just 5 minutes ago, we became aware of the fact that on one particular website, the order of our keynote presentations is switched, and there are people waiting to hear the James Webb program, and we don't know how these other websites are getting out there. I mean, nowadays you can write scripts that create websites from scraping other websites and so forth. We don't know where all of these pop-up contest sites are coming from. We are not creating them. Okay. Our website is the definitive. I mean, we have the Bob. Okay, so we have the Bob website as well. So just be aware that if it doesn't come from us, it's not official information, okay? And this is a new phenomenon. This has not happened before, so we're not sure what's going on, but we'll see. It's there. Well, to my knowledge, those QR codes weren't published until yesterday. So well, they've been popping up over the last 2 weeks or so. We've been getting emails about them. So we'll see what we can do about that. So, our next speaker, I thought, was a Bobfest newcomer. And as Ron White said, I was wrong. He is a Bobfest, well, you're a regular now. This counts as being regular now. And it's even better because he grew up right here in North Carolina in Shelby, which I believe is the liver mush capital of the world. And if you don't know what liver mush is, you probably don't belong at Bobfest, okay? So, might want to do a little bit of research there if you're new to this region. His name is Michael Renberg, and he is a meteorologist working for the National Weather Service in the Greer, South Carolina office. He's a native of North Carolina, grew up watching the sky from the quiet countryside of western North Carolina. We all love it here. His passion for the sky extends not just to the weather, but to astronomy as well. There's a very intimate connection there. I'm sure you are aware of the curse of the new telescope. If you buy a new telescope, the number of cloudy nights goes in, I don't know what the exact exponent is, but it goes in proportion to some power of the size of the telescope.
That's actually a law of physics.
It is, yeah, and I bought a 10-inch Dob last summer, and it was cloudy sorry about last August, that was my fault. But in addition to being a professional meteorologist, he's an avid amateur astronomer, enjoys late nights in the backyard with his telescopes, as we all do, almost as much as he enjoys forecasting the weather. And he told me something that startled me as we were chatting this morning. He told me that meteorologists can't control the weather. I mean, what's up with that?
There goes your raise.
But that's okay, because we can't control the skies any more than those guys can control the weather. So please give a big welcome to Mike Renberg.
Thank you, and good morning, Bobfest. I talk pretty loud to begin with, so if I start blowing anyone's eardrums out with this mic, just go ahead and give me a yell to keep the volume down. It might be necessary at some point. So as I've been introduced, I'm a meteorologist, but I'm also an astronomer. I thought twice about how I was going to be received today, because let's face it, I'm a cloud guy in a room full of people who hate clouds. It feels a little bit like poking the bull, but as Joe said, I am also an avid amateur astronomer. I own multiple telescopes, and as my wife will tell you, I spend way too much time out in the backyard doing everything from observing to photography. And so because of that, I'm intimately familiar with the kinds of challenges that even a clear sky can present in this hobby. And so the techniques that I'm going to be sharing today are not just some theory that came out of a textbook. They're not things that I had to think about to come up with for this presentation. They're tried and true methods that I use myself every time I'm taking my telescope out for an observing session. So I'm going to take a really bold stance here for somebody whose livelihood is predicated on the atmosphere. And I'm going to call the atmosphere a little bit of an enemy for those of us who own telescopes. You might think that the air is see-through, it's effectively invisible, so it's not having too terribly much effect on light passing through it from space. Right? Wrong. There are actually quite a few processes that the light traveling through our atmosphere undergoes before it reaches our eyes. And most of these have a net degrading effect on what we see through our telescope. And so sometimes the atmosphere does feel like a challenge to overcome, at the very least. So what do I mean by that? I present to you two images of Jupiter, both taken from my backyard about maybe 2 weeks apart. It's been about a year now since I took these. The first has not too terribly much detail. You've got some cloud bands, a little bit of good color in there, but beyond that, not a real lot of detail pops out. This image was taken with an 8-inch f10 Schmidt-Cassegrain using an ASI 224 CMOS camera. The image on the right is also of Jupiter, and it has a lot more details. You can see everything from cloud bands to a couple of the Galilean moons or in orbit, and if I'm not mistaken, the Great Red Spot is even faintly visible there on the surface. So, this image was also taken with an 8-inch f10 Schmidt-Cassegrain. The acquisition details as well as the processing details of these two images are very, very similar. And so why do we have this huge difference between the end quality of these two images? I am humble enough to admit that part of that difference comes from my subpar skill with post-processing, that is. I'm more of a deep sky guy, so when it comes to planetary astrophotography, I'm probably not the best person to process an image. But I am positing that a large amount of the difference between these two images comes from the condition of the atmosphere when they were taken. This first image was taken the first night after a cold front had rolled through. There was still some residual moisture in the atmosphere and a lot of turbulence, and so that was severely degrading what we call atmospheric seeing and transparency, and we'll address each of those shortly. And the image on the right was taken under stagnant high pressure, very dry, nothing going on aloft. And so the end quality was much better because these factors of seeing and transparency were themselves much better. There we go. Maybe I need to stand up more in front here so we can see me. So to understand what these processes are, I think it might be helpful to start with a generic understanding of how light moves. You may or may not have heard of the wave-particle duality of light. The details of what that actually means are better left to a quantum mechanics classroom, partly because you could fill an entire semester with it, and partly because I have no idea how to explain it. The end result, though, is that light behaves as a wave. And so what that means is, and this was alluded to a bit in the last presentation, light diffracts, which means it bends around corners and bends through openings. And I want to specifically highlight the bends through openings part of that statement, because you can think of the objective lens of a telescope, you can think of the opening at the front of a Newtonian reflector telescope as an opening. You can. This died. It's okay. Can everyone hear me if I yell?
Sure. You can use the podium.
Get that one turned up.
Yeah.
He's got to turn it up. Not for that, for the other wireless.
I could try using this one. Yeah.
Go ahead and try this.
All right, let's do that. I'll stand with the podium.
Yeah, there you go. Just stand in front of there.
All right, is this better?
Oh, yeah.
Excellent. Okay, so as I was saying, light bends through openings, and the front end of a telescope can be considered one such opening. And so the practical effect of this is that light bends merely through the process of entering a telescope and making it to your eyes. And so this results in what we call this airy disk around stars. So even though we tend to think of stars as point sources of light, and in truth they are point sources of light, but as they diffract entering the telescope's optical tube, they spread out in much the way that these waves are depicted as spreading out around this opening here. Light does the same thing, and so we get this kind of smeared pattern, which again we call an airy disk. Now this happens independent of Earth's atmosphere. This is part of the physics of light itself. The term airy actually comes from the name of the gentleman who first mathematically described these, Sir George Airy, who did his research in the late 1800s. So now if you've ever heard the term diffraction limited, when referring to telescope parts, this is referring to the notion that diffraction is what limits a telescope's resolution, right? You cannot make an image through a telescope sharper than what the physics of light allows. There is no adjustment that you can make to the optics or your focus that is going to get rid of this airy disk. And so in theory, this is a good thing because it means that the optics of your telescope are quite perfect. In reality, however, diffraction is rarely the factor that most strongly influences your limiting resolution, because in real life, we have an atmosphere. And the atmosphere, as I've said, produces a whole lot of unsavory effects on light as it's moving through our telescope. And so a few of the important ones that we're going to discuss today are scattering, absorption, and refraction. And we're going to talk about each one of these in turn. So in this image here, which I may or may not have stolen from a popular record label from the mid to late 1900s. Different discussion for a different day. We can see the refraction of light. Refraction fundamentally means that as light enters some medium, be that glass in the case of a glass prism, be that air in the case of our atmosphere, it bends. And the particular way that it bends has to do with the way that the medium is moving. In the case of the air, it's a result of changing density as winds blow at various locations in the atmosphere. So picture this. You're standing outside on one end of this building. You're probably going to feel some particular breeze. It might be a light breeze blowing in a particular direction. Stand over on the other end of the building. You're going to feel a completely different breeze. If you stand on top of the building, which I don't recommend doing, you're going to feel another breeze entirely. And the same goes for if you stand out in the parking lot or out on the street somewhere. So the idea is that the atmosphere's currents, the winds that are blowing, and as a result, its density changes significantly over small distances. So now extrapolate that. The atmosphere is many miles deep, and you have a very, very complex system. Every time the light encounters some new density current, it bends in a different way. And so the light doesn't travel straight from space to your telescope. It zigs, and it zags, and it zags again, and then it zigs. And every second, as the distribution of winds in the atmosphere changes, the path that light takes through the atmosphere also changes. And so this manifests as a constantly changing distortion that you can see when looking through your telescope. If you've ever looked through a telescope at Mars or at Saturn, something most visible in my opinion when you're looking at planets on a night of poor seeing, it might almost look like you're staring at a coin at the bottom of a wishing well. And in fact, the rippling effect that you get at the bottom of swimming pools and wishing wells is the exact same process. As light is moving through that water, the currents in the water are physically distorting those beams of light by way of refraction. And so the atmosphere does the exact same thing. It just takes a lot more atmosphere to do it than water, because the atmosphere is less dense than water. So it all goes back to density. And so in fact, the twinkling of stars, which is technically called scintillation, but they're twinkling. The twinkling of stars can actually be a gauge for how bad that turbulence is and how much refraction and distortion is occurring. So even though we typically think of twinkling stars as kind of this stereotypical part of a clear, pleasant night out, you can go outside and gauge how bad things are going to look through the telescope by how much the stars are twinkling. If you step outside and the stars are twinkling like crazy, that is a sign that there is a lot of atmospheric turbulence that will be more strongly distorting images through your telescope. If you don't see any twinkling at all, that's a sign of excellent seeing and far less distortion that will be visible through the telescope. I think I was pointing it the wrong way. So, where does turbulence come from? The aim here is to forecast it in advance so that if you're trying to plan an observing session, you know what to expect from the sky. And so fundamentally, we are looking for these atmospheric features that cause turbulence, that disturb the air. And now this is by no means an exhaustive list. There are any number of features that you could point to that might help distort the air. I've isolated a few that are fairly easy to forecast and that I think might be most useful in predicting atmospheric seeing. On the large scale, we have things like jet stream winds, frontal boundaries, which we'll talk about first. And then on the smaller scale, which is much harder to predict for reasons of the way our weather models are configured, small scale factors like friction, like heat currents, and even convective turnover associated with thunderstorms can also severely impact your turbulence. So if you could take a entire hemisphere's worth of wind, what you would see is, on a very large scale, 3 cells of air, they call them. And each cell is kind of this overturning pattern that exists from the Hadley cell runs from the equator up to about 30 degrees latitude, and the Ferrel cell from there up to about 60 degrees, and then the polar cell near the poles. So what's happening here is that the equator starts out warmer than the poles, simply because it gets more sunlight. This is true for pretty much the entire year. The atmosphere does not like being out of balance, and so all wind is trying to do when it blows is to relieve these differences, to get rid of these imbalances and get the atmosphere back into perfect balance. The rotation of the Earth, as well as things like terrain and the ocean, tend to disrupt these winds. And so you wind up with these separate cells. And it turns out, by way of some very advanced math that I probably couldn't explain if I tried, you get at these boundaries between air masses strong winds aloft, which we term jet streams. So if you've ever heard about the polar jet or the subtropical jet on the news, this is where these are born. They are born at the boundaries between these broad hemisphere-scale air masses. And they can be very, very, very fast. So for example, this is a model output image of the jet as it crossed over our area middle of last week. And these dark yellows here signify 160 plus knots. So we're talking about very fast winds. These are winds that far up in the atmosphere, jetliners can hitch a ride on to make your flight experience faster. So this is no joke in terms of fast winds. And as a consequence of that, they produce a lot of turbulence in that part of the atmosphere. They can produce all kinds of turbulent eddies, especially along their boundaries here. And exceedingly fast winds themselves can cause a huge boom in refraction of light as it passes through the air, even through the jet core. And so, for example, from this image, this was from Wednesday evening. We had a jet directly over us. So were you to step outside, it was fairly clear, it was starting to clear up overnight at least. Were you to step outside and look at the sky on Wednesday night, the seeing would likely not have been that great. I went outside with a pair of binoculars before I went to bed that night, and it didn't appear to be that great, although I didn't take a whole telescope outside to see if Saturn and Jupiter were rippling. By contrast, if you had gone to, say, my former home of Champaign, Illinois, well, there's nothing going on up there. There is no strong wind aloft, and so the turbulence, and thus the seeing in Illinois, would likely have been much better. And so I'll show you some sources later in this presentation where you can go to pull up these maps for yourself and try to diagnose where turbulence might be worse. Another factor that can severely impact turbulence in the atmosphere is fronts, and these are boundaries between smaller scale air masses. You'll often hear in the news about a warm front or a cold front passing through your forecast area. And in truth, warm fronts are typically too cloudy for it to matter. But the cold fronts in particular, you'll often get your rainfall and your cloud cover out just ahead of the front, and it'll start to clear up, but the actual frontal boundary will not have passed by yet. So, for example, this cross-section is a little bit difficult to interpret, but the blue shading here represents the actual frontal boundary. So this is where you would expect your rain and your clouds to be. Notice, however, that these tightly spaced contours here, which represent turbulent air, exist behind where the brunt of this frontal activity is going to be. So it would likely be mostly clear in this region, but if you stepped outside and looked at the sky, the turbulence would nonetheless prove that there was still an effect from this frontal boundary, and it would not be a night of good atmospheric seeing. And my picture of Jupiter from earlier is proof of that. So one of the smaller scale effects is something we call urban heat island, and this is best understood as cities being warmer than the surrounding countryside at night. And there are a variety of reasons why this happens, ranging from more homes and automobiles producing heat to the fact that cities tend to be filled with things like asphalt and pavement and sidewalks, things that absorb heat readily from the sun, at least compared to dirt and grass, and then have to re-emit it at night. And so this manifests as heat currents that are more turbulent and more chaotic over cities during the night than oftentimes the surrounding countryside. And this one is a little bit harder to predict than your large-scale features. This is not something that models tend to handle well because it's so small scale that they just can't pick up on it very well. But the general rule of thumb here is that the hotter the day and the sunnier the day, the more heat these surfaces will have absorbed in your cities, and thus the more they will have to release back out at night. So it's kind of a give and take in that sense. And then the last one that's worth talking about is friction, which is intuitively understood as drag with the ground. This has multiple effects. We can kind of logically conclude that it's going to slow air down near the ground, especially the more uneven terrain, the more obstacles, trees, and things you have on your terrain. The more of we call this a speed shearing impact, where winds are slower near the ground than they are aloft. Incidentally, through another stroke of mathematical magic, we can also change the direction of winds by slowing them down. And so when you get this speed shear, you tend to also have a complementary effect of directional shear. And so wind might be blowing one direction at the surface, whereas just above the surface, you have it blowing in an entirely different direction. We call that directional wind shear. And so, yes, as I pointed out up here, the more uneven the ground, the worse the frictional effects become. With that being said, even somewhere very flat, like the Great Plains, will suffer to some extent from terrain shearing and drag effects. So then the next thing I wanted to talk about, and this is not really a feature of the atmosphere per se, but it's this zenith angle concept. And this is something that comes intuitively to a lot of people who use telescopes. It's this idea that the closer something is to the horizon, the worse it's going to look compared to something directly overhead. And then that's because you're physically looking through more atmosphere if you're looking at an angle at the same object. And so from a refraction standpoint, that's effectively saying, okay, well, you now have more air to distort your light. You have more opportunities for it to change its path and bend as it's moving from space to your telescope. And so these distortions become worse. But this doesn't just apply to a refraction perspective. This applies to something else called atmospheric extinction, which in meteorology is really a blanket term for multiple other processes. The root idea behind extinction is that we start out with light of a certain intensity, and then in the process of moving through the atmosphere, some of that light gets lost. And so by the time it reaches our eyes or our cameras or our telescopes, that light has a lower intensity. It's not as bright. This is often a subtle effect that you can't pick up on very well with the naked eye, but it often does make a major difference for photography. And so two of the major ways by which this occurs are scattering and absorption. So scattering is a wavelength-dependent process by which light coming from one direction hits a particle of some sort. It can be an air molecule, it can be some kind of dust or soot suspended in the air, it can even be water vapor. And instead of reflecting off in one direction, it scatters off in multiple directions. And so if the light's coming from this direction and you're standing over here, you're only getting the portion of light that gets reflected toward you. And so all of this other light that scatters off in different directions never makes it to your eyes, to your camera. And so as a consequence of that, you've now lost some of the intensity of your light. And so this varies not just on the way the air is moving, but on the size of the particles doing the scattering, which makes it more complicated for reasons we'll get to shortly. Absorption is another subtle but nefarious process, and this takes place when light is physically absorbed into molecules. So this is different for every molecule because it depends on the particular electron configuration of the molecule. And so this can kind of be likened to the emission spectra that you will see for various nebulae and things like that. Each one of these lines represents a particular wavelength of light that is absorbed upon passing through our atmosphere. And it is absorbed upon passing through our atmosphere by a particular gas in our atmosphere. And so what's important about this is that it's completely dependent on chemical composition. So if you have different things in your atmosphere, your absorption pattern might look a little different. And so that makes it very, very difficult to forecast extinction quantitatively, at least. Though we'll talk about a few reasons or a few ways that you can forecast it qualitatively. So for the mathematically inclined, this is a curve describing how extinction responds to zenith angle. The idea being that it barely responds at all down to about 60 degrees. So from straight up all the way to about 60 degrees of zenith angle, you're not seeing much of a change in your extinction. But then as soon as you get below that, the amount of extinction skyrockets, and you start to lose light at a very, very fast rate, which again severely impacts your view through the telescope. So, transparency is a direct effect of this extinction effect. Transparency occurs because particulate matter, especially water vapor, but also dust, smoke, any kind of particulate matter that can be suspended in the atmosphere, absorbs and or scatters away the light that is passing through it. So this also has a side effect of refraction through liquid drops, but this is less prominent than for some of these other effects. The problem with forecasting transparency is that this doesn't depend just on the motion of the air, which can be modeled really well by fluid dynamics. So we're no longer just talking about the dynamics, but because we have this size dependency, because we have this size dependency, because we have this chemical composition dependency, because we have dependencies on all of these other things that relate to the particular distribution of what chemicals are in our atmosphere at the given time, we no longer have the ability to just plug it into a model and see what happens. In fact, to my knowledge, there is no statistical model that can accurately produce transparency forecasts at the level of fine detail that we require in order to use it as astronomers.
What is Doppler? What does it do?
Doppler? So Doppler is an effect used by our radars, and that's used to measure larger objects like hydrometeors. So think about your rain droplets, your hailstones. And so our radars are picking up on much larger objects like that, and that's used in order to detect things like clouds. Rainfall. It can even be used to differentiate between what type of precipitation is falling. So if you are really willing to dive into the data that comes out of Doppler radars, you can even pick out the difference between rain and snow and sleet, which even then is subtle and difficult to do. But that's also something that is not modeled well as a forecast. It's more of something that you can look at in real time. And so that's kind of tangentially related to this, but it operates on many of the same principles, but it doesn't help us produce forecasts, if that makes sense. And so transparency fundamentally is just such a complex model to try to build that it's best understood qualitatively than quantitatively. That is to say, we don't really have many good models that can tell us, oh, this is what the transparency is going to look like tonight. So instead, we want to focus on some of the particular substances that can cause degraded transparency. Just jumping all around today. So one of the best ones of these is this moisture through the column idea. And the particular parameter that we can use to diagnose this is something called precipitable water. Now, there are a million different ways that you can look at water vapor or liquid water suspended in our atmosphere. You can look at the relative humidity at a given height. You can look at the relative humidity over a layer. You can look at the average humidity or the dew point. There are just so many, there are thermodynamical parameters that we've made up to make our own lives more complicated in meteorology. But in my opinion, one of the best ones for this purpose is to look at this precipitable water, because rather than looking at a particular level, it sums up the water that's present over the entire atmosphere. So it's this vertical combination of everything. And if you think about it, it doesn't really matter as much where the water vapor is, whether you have water vapor way, way up in the atmosphere or whether it's closer to the surface. It's still going to cause the same absorption and scattering impacts regardless of where it is. So we're more concerned about the total amount. And so, for example, from this forecast chart that I've shown here, this is also associated with the front that passed through middle of this week. And so in this area here, this kind of purple and blue banded area, this is where you have active rainfall. Whereas farther to the west, it was starting to clear up, but these PWatt values were still quite elevated. And so that signified a lot of residual moisture still trapped in the atmosphere behind this passing front. And so this represented, again, a degradation in these transparency values that would have manifested, for example, as dimmer, fuzzier, more difficult to focus objects. In my experience, seeing tends to impact planetary photography the most, whereas transparency will affect deep sky photography the most, because you're operating with deep sky objects on so little light to begin with that when you bring in these transparency effects and extinct some of the light that you already barely have enough of to begin with, it only compounds a problem that you already have to deal with. So again, that's been my experience in this hobby.
Question, the number
Sure.
down, is that the barometric pressure that we're seeing where bars 95 or 96?
Yeah, so these represent, if you were to take the moisture in this column, condense it all into liquid water, and then drop it as rain, how much rain would be produced. It's kind of a confusing way to look at it. But the general idea is that if you have, say, above 1 inch of precipitable water, you likely have clouds and rain ongoing. If you have less than, say, 1/4 of an inch, so like these browns and these dark colors here, that signifies clear, dry air. And then these kind of in-between values of less than 1 inch tend to signify a lot of moisture in the air, but you're not necessarily dealing with clouds, certainly not rainfall. It just may be clear, but moist.
What about the numbers on the map, like 996 and the 1000? Because I see like 1,000.
Sure. Yeah, so those are your, we call it the mean surface level pressure. So that's, you're effectively taking the barometric pressure and you're correcting it for terrain, which is, again, a confusing process, but it's a much less ugly map to look at than the raw barometric pressures. That's a lot easier to interpret. So yeah, a lot of times you will see in these forecast maps, and some of them that I'll show later the same way, you'll see these things being overlaid with either surface winds or surface pressure. Dear Lord. Here we go. So dust and smoke. So once again, we don't really care how high in the atmosphere these factors are occurring. We're mostly concerned with how much there is total above our viewing location. And this is another one that's very difficult to quantify. There aren't a real lot of models that are out there, at least that I'm aware of, in my operational position, that can model these things like smoke and dust and soot and particulate matter. One of the best tools, and I've linked to it at the end, one of the best tools there is this per smoke model. And this is, again, vertically integrated, meaning that like this precipitable water, it's through the entire column telling you how much you have total without much of a explanation of how high in the air that particulate matter is. But so, for example, you can see these little plumes here. Most of these plumes, they correspond to wildfires that are ongoing. And so what you're seeing are these plumes of smoke and soot that are traveling downstream from where the wildfire is occurring. And the HERD smoke model is a very short-term model, so you can't really use it more than 24 hours in advance of an observing session, but it's certainly something that if you're planning an event, or planning a session rather tonight, you can still get some insight from. Luckily around here we don't have to worry about significant smoke events too terribly often, but when we do, this tool comes in handy. So the last, I guess, weather impact that I wanted to run through, and then I'll actually walk through a example forecast, how I might go through the process of determining what an observing session might look like. The last factor that I wanted to go into is dew, because I don't see how any discussion of the negative impacts of weather on astronomy would be complete without describing dew. Imagine by the giggling going on, most of us have had one of those nights where you set up your telescope, got it running, maybe you're doing some long exposures, and you come out and, okay, the last 30 minutes of your exposures have been completely ruined by dew that formed on your primary or your objective lens. In my experience, that is the single best example of why you should get a dew heating strip. Because dew forms from the process of condensation. So you start out with water vapor in the air, cool it down enough, and it will condense into liquid water. So if you think about what primary mirrors and objective lenses love to do when you let them sit out in your yard for a while, they get cold really fast. And eventually they get so cold that as soon as some water vapor touches them, it just condenses right onto the surface. And unfortunately, the ingredients that it takes to get dew are moisture near the surface, which in this part of the country we virtually always have, and clear, dry conditions above the surface. If that sounds familiar to you, it sounds familiar because it's what I just described as optimal conditions for good transparency. So unfortunately, on a night when you want to go out and observe, the odds of getting dew are high. And so in my opinion, dew is certainly something that you should understand and be prepared for, but the reality of dew formation is that it's going to happen, and it is best left as something to be ready for and combat, rather than something to plan an observing session around, like some of these other forecasting techniques. And so these are a few of the sites that you can use to actually do the forecasting that I've described. I wonder, is there a way that I can click on some of these links and just bring up a couple of example maps?
I'll try.
I think I got about 5 minutes left.
Which one?
Let's pull up tropical tidbits. Can everyone still hear me? Just talk at the top of my lungs. It's something I've always been good at. So,
I think you gotta turn up, get out of the PowerPoint.
oh still, yeah, I bet it's in presentation mode.
Yeah, take it out of presentation mode.
Put a fresh battery.
There it is.
Oh, excellent. There we go. Awesome. Okay, excellent. So most of these sites are very similar. They have a lot of different color schemes, and in my experience, people who use them just kind of find one that they like the best. But you can look at all of the same data on each of the sites that I've provided. I prefer tropical tidbits because it's what I learned to forecast on. I will tell you that one of these other sites, this pivotal weather site, has a lot of the same data, but it has excellent color schemes for people with red-green color blindness. One of my best friends is red-green colorblind, and whenever I'm sending him things that at least I think are neat from a weather model, I have to be careful to send it to him from pivotal weather, because if I send it to him from certain other sites, he won't be able to tell what he's looking at. So when you go to one of these sites, you want to bring up your forecast models, and then you can kind of just cycle through some of the same products that I've run through in this presentation. So for example, the first thing I mentioned were these high-level winds. And this is labeled here as 250 millibar winds. For those familiar with pressure levels, millibars represents, or 250 millibars represents the pressure well above the atmosphere, or well above the surface, and high up in the atmosphere. 250 millibars often corresponds to as high as 25,000 feet above the ground, or higher. But again, it varies. And so you want to pull up this map and just look for some of the features that we've run through. So once it loads, I will point out what I mean.
Astronomer alert that says ding, ding, ding.
Unfortunately, no, but that is certainly something that I will bring to my superior at the Weather Service and tell them that we need it. It's
Like the aurora alert.
Yeah. Now, there is a pretty good resource if you're interested in things like aurora and space weather. For those who may not be familiar, there is a Space Weather Prediction Center that is part of the National Weather Service, much like the Storm Prediction Center, the Weather Prediction Center. And you can find that online, and they have aurora forecasts and all sorts of things. So maybe I'll show you that since this doesn't seem to want to load. Yeah, so fog forms under very similar conditions to dew. You have excellent low-level moisture right at the surface, and then you have dry conditions aloft. And the reason that that works is because fog, like dew, requires colder temperatures to form. And the clearer and drier it is aloft, the faster it can cool down. So yeah, fog is very similar in that respect on forecasting sense to dew formation. So this is the space weather prediction page. Normally there would be some things highlighted yellow here to signify impending solar events, but it looks like the sun is pretty calm. If you're ever bored though, it's a lot of fun to jump on this website and look for the aurora forecast. I'm not quite as familiar though with this.
So it'll tell you whether it's going to be a good aurora or a...
Yeah, so for example, this is a aurora loop here, and these color shadings represent the probability of an aurora forming. Yeah, it's not cooperating. Oh well. Regardless, the general idea is that essentially these satellites, like I think a good example of this is the SOHO satellite that's measuring the energy coming off of the sun. And again, this is not my area of expertise, so don't take my word as gospel here. But my understanding is that we can use this information coming from these solar satellites to predict the way that solar emissions are going to interact with our Earth's magnetic field. And it gives us a window into the activity of aurora in the near future.
So it covers both the South Pole and the North Pole?
I believe so.
So we can be bipolar?
Stop it.
All right, I don't think I can top that one. I think on that note, I'm going to call it a day. Thank you all for having me.
As a freshly retired physics professor, there's been a lot of good physics in both talks today, so I'm very appreciative of that. Thank our speakers once again. So you both are welcome back at any time. We are on schedule. It is now lunchtime. Food is great. A couple of things. If you go outside and go up the sidewalk there, you will see...
Yeah, past the greenhouse and handicap ramp, I'll be standing at the top of the handicap ramp pointing people.
This is John Lovelace. He'll have a sign that says food trucks. Okay, follow him. For those of you who don't want to follow him, they're in the bus parking lot if you're familiar with the campus here. Also, if you are a presenter, in either the morning session or the afternoon session. See Jeff Wisnut, he will give you your lunch money. Okay?
Quarter this year, I think, right?
I think so, yeah. Be back in this room, please, at 12:45, so we can give you the corrected version of the afternoon schedule. Okay? So please be back in here at 12:45, Brian.
You got it.
Oh, we will have a van for people who need help with mobility issues. Dwayne Strelo from the Science Center will be driving that to the food truck.
So please, just meet out here by the registration desk as soon as possible so we know what we need to do, where this van goes. So just meet right outside these doors.
Well, comment or a question. If you want a good sausage dog, beef style, Digging Dogs is awesome.